started. Once we have v sub 1, then these are all, we have the current values, and we can calculate at n equal 2. And then so on and so on, just like we've done before. But we have to do both equations. Before we just had one equation, now we just do both. So really not so bad, okay? It does get a little tricky as you get more of these, and that actually motivates how I want to slightly rewrite these in terms of matrix notation. And so the matrix notation that I have is, well, I'm just going to write this as a matrix, okay? And so we'll start doing this a lot, and hopefully you're okay with this. Let me pull this down here. So what I'm saying is I would write this first column. So I have v of m plus 1, I of m plus 1. There's a column matrix. Is equal to some matrix, some 2 by 2 matrix. And this would be v sub n and I sub n. So there's the current value and the previous value. You say, what goes here? Well, I'm just rewriting these equations. So you can see this. In this case, this would be, looks like it'd be 1. Right? This would be delta t over c. There's the first equation. And then the second equation would be, I think I lost an L here. Apologize. Right, when I brought this over, I divided both sides by L. I got my L there, but I didn't get my L here. So it's there, there, and so now when I write my equation, this is negative delta t over L, and then the I sub n is 1 minus delta t r over L. It's a little small, but maybe a better black. Okay, so I might call this, for example, I might call it beta m plus 1, and this is a column vector. And then I might call this some B, that matrix B. And then this I would call beta n. And that looks a lot like what we had before when we weren't dealing with 2 variables, just one. But we know I'm kind of cramming them both in there in a column vector. Okay, and then it's easy to see all the, if we started doing a program, you'd have beta 1 is equal to b times beta 0, right? That's the first step. There's the second step, which is beta 1, which obviously I could write this. Here's my matrix squared times beta 0, and so on. In fact, if I would write the code for this one, I could do beta n. If I wanted to write it in this, I could do it various ways. But this one actually comes out nice, just like before. If I look at that nth value, I take the initial condition. I have to multiply out that vector, that matrix n times, and that'll give me the nth value. Okay, and I think I have the code for this, and I will insert the appropriate slide. All right, for this next section, I want to take one step further, and I also want to show the implicit method in this example. I have put implicit and explicit I want to get us in the mood for writing things in matrix notation, okay, for these systems. So I'm going to use a little bit more of that. One thing that I didn't mention in this last section that I do want to bring out is if we come back to our RLC example, you know, I wrote down the equation and then I just directly wrote down this numerical solution, and that's fine. That's fine. One thing, I could have written it down a little different way, in which is a way that maybe is more appropriate or reminiscent of your differential equations class. Okay, so this is really just a small point, but I just want to make this connection, and then it maybe gives some practice and getting used to seeing things in matrix form. Okay, so what am I going to write here? I'm going to write the same thing that I wrote before. Okay, so here's the two first order equations. Okay, and frankly, if you were, you know, we could solve this. You solve it in 2030. We could solve for it exactly for this example, right? A lot of times I like to take examples that we know how to solve and show you how you do it numerically, and then we can apply those to situations where we don't, right, for nonlinear equations and whatnot. But there's the exact, you know, the differential equations that we would have for this. So normally I might write this even, you know, from a differential equation standpoint. Here's my system of first order equations. If I wrote this in matrix form, and I could write like this. Right, and then here's my v sub c, here's my I. And so here's my first equation for this system. That would be a 0 here. I'm just looking up here, right? And then this would be 1 over c. And then for my second equation, I would get negative 1 over L. It goes with the v sub c. And then I get negative 1 over r. Okay. And maybe I would call this matrix A. And I'll do the same thing. This little column, I'll just call it beta. So obviously, one way I could write it, this system here, is like that. Okay, and I put the little squiggly here. Maybe I have to be a little careful. Maybe I should put like a hat or something like that. Just to indicate that it's a column vector. Sometimes I might put indicate that's a matrix, but a lot of times I don't do that. Okay, and I know that that column vector is the v sub c. But obviously it's much more compact once I define that. So that's a way that I could write the actual system of differential equations. I mean, that would be your starting point. You got a problem, you knew what the, you know, you got the first order system, and that's how we might write it. Now the question is, how do I make it numerical? And so I want to just keep with that notation and talk about explicit, implicit. So this is what we just talked about. There's explicit. And so for the explicit, I might write it like this. I might write it as, maybe I could even put a tilde there because this is approximate. Right. Divided by 1 over delta t. There's my first order. And there's my A, B. In this guy, it's explicit, so it's n. And obviously what I would do here is I would solve for b to n plus 1. Okay. We could code that out too. I'm going to write it one extra way. Now we have to be careful. I mean, these are not scalars. These, we're working with matrices, and so I'm going to factor this out. But I need to make sure, here's my matrix times this column vector. Okay, which will give me a column vector. Here's just the column vector. So the minor point in linear algebra is that I could write this, I could put I here. Now here's the, there's no perfect notation. And so maybe to emphasize that this is not current, I'm going to make it like that. And you say, well, what is it? Well, hopefully you already kind of know. It's the identity matrix. Okay, so there's the identity matrix, and we know we can multiply in matrix operations. It's like multiplying by 1, right? You multiply by the identity matrix, you get the vector back. It's easy enough to verify. So now, here's my minor point, is that I could write this as this identity matrix plus delta t a, and there it is. Okay, so there's my recursive relationship. There's my recursive relationship. Okay. And obviously before I had like b, but that, you can check it. That goes back to the if you combine this, you get the B matrix that we wrote before when we were doing this out. Okay, so there's that B matrix. There's the 1 that comes from the identity. There's the 1 there from when we add in the identity matrix. Okay, so that's fine. Now let's do implicit. This is a nice review. So this is Euler. That was Euler explicit. This is backward Euler, or maybe I'll call it the Euler implicit. My blacks are not doing so good, so I think I'm gonna, hope it's not too distracting, but I'm gonna switch to green. So with the implicit method, we know that we have on the left-hand side, we have our approximation for the derivative, first order derivative. So there it is. We know what beta is. We know beta is v sub c I, right? And so we know we're looking at the nth time, and the n plus 1 time. And we'll lose a, because that's what we used when we wrote down the system of linear equations. And this is now beta n plus 1 because it's explicit. Okay. Now this is kind of, this gets to the heart of explicit versus implicit. I can still solve for this particular system. I don't have anything that I can't solve for. But you're going to already notice that there's a bit more computation involved in the implicit. Okay, it's still not overwhelming here for this smaller example. But let me illustrate what it is.